Assalamualaikum and hi. We are from group 5. So for this project, we will present about the topic arithmetic operation. Okay, so this is my team members. The first one is Muhammad Shahmi. The second one, Nur Sabania. The third one, Nur Hanim Shaida. And the last one is me, Farshahira. Okay, for content, we divide it into 4 parts of topics which are 4-bit division, which will presented by Shahmi, 4-bit addition, which will presented by Sabanya, 4-bit subtraction, which will presented by Nurhanim, and finally 4-bit multiplication that will be presented by me. And for each section, will have its own subtopic, which are introduction, objective, methodology, VHDL codes, result, and finally the conclusion.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shahmi. First is introduction for 4-bit division. First is importance of arithmetic operation in digital design is they serve as the foundation for digital design supporting a wide array of applications. Evolution of digital system is to meet complex demands. Division operations are crucial as digital systems evolve. This evolution aims to achieve computational accuracy and efficiency. The focus is on exploring methods and challenges in creating an accurate and effective digital circuit. Basic arithmetic operation, addition, subtraction, multiplication, and division are foundation for digital system. Division is like essential for computation and algorithm in various fields like signal processing, computing, and control system. And last is processing and dividend numerical value is crucial in signal processing, general purpose computing, and control system. The next is objective. The first objective is to develop an efficient algorithm circuit for division to 4-bit binary number using VHDL. VHDL is VHSIC hardware description language. The second objective is to use VHDL to describe the behavior of the 4-bit division circuit and ensure that division circuit produce accurate result for various input scenarios. The last one is document the entire design process including VHDL code, simulation result, and implementation details. The next slide is methodology. First is arithmetic operation including division form the basis for various applications in digital design. Division become crucial for computational precision, particularly in the face of increasing complexity in digital systems. Next is exploration of design, implementation, and validation of a 4-bit division circuit using VHDL. VHDL is employed for its methodical approach in modeling digital circuit. The use of VHDL introduced the goal of building a high-level model for the 4-bit division circuit. This model serves as an actualization of the algorithm capturing the complexity of digital arithmetic. Next is achieved through structured VHDL modeling. Validation process includes comparing simulation outcome to mathematical prediction. Last is tools such as code editor, hardware testing equipment, and VHDL simulation tool are utilized through the methodology. This is VHDL code for 4-bit division. In the left is for the coding. As you can see, library. Then at the right is example of the test branch. We paste the code into the software that I use. The software that I use is Xilinx Vivado. This is the result for the coding that I paste into the software that I use. The software that I use is Xilinx Vivado. The test case involve dividing two positive 4-bit binary number A 0110 6 and decimal and B is 0101 5 and decimal. The first point is initialization phase. Initially, it is 0. Inputs A, B start not based on your test blank. Clock and receipt signal may be initialized. Start of simulation. Start signals go high. Start is exit at 1. The division operation begins. The next is division process. During each clock cycle, the division process takes place. Internal signal result are updated based on the logic. The process continues for the required number of circuits. Complication of division. Down transition. Once the division is complete, equal to 4, transition from 0 to 1. The transition indicates that division operation has finished and the results are valid. The next is stable state. The Riemann height. The Riemann height equal 1 until further test band action or the end of simulation. The outcome verify that the VHDL bit division is functioning correctly, particularly test case. As a conclusion, the division of VHDL for bit division has provided a true education in digital design. The importance of VHDL is emphasized in implementing arithmetic operation. The organized use of entity and architecture is highlighted as a crucial aspect. The implementation of SQL logic and process is explored within the VHDL framework. The significance of simulation and testbed in refining digital design is recognized. The essay addressed the difficulty encountered in debugging and troubleshooting. VHDL practice utility in solving real-world issues is showcased. The value of testing and verification process is emphasized for reliable digital design. Strict procedure underscore for ensuring error-free digital design. Last one is outgoing education and preservation are emphasized as essential for proficiency and digital design. That's all from me. Thank you.
4-bit addition involves adding two 4-bit binary numbers together. Each bit in a binary number represents a power of 2, and the addition is performed similarly to decimal addition. A 4-bit binary number consists of 4 binary bits, and adding two 4-bit numbers involves adding corresponding bits while considering any carry from the previous bit. Understanding and implementing 4-bit addition is not only foundation to digital design but also serves as practical illustration of binary arithmetic concepts. It encapsulates the essence of parallel processing and digital circuits, offering insights into the efficient execution of arithmetic operation within the binary domain. So these are the objectives for 4-bit addition, which is the primary objective is to design a 4-bit adder circuit that can accurately perform binary addition on two 4-bit binary numbers. The second objective is to define input and output ports for the 4-bit adder entity to allow external connections. And the third one is to ensure that the design adheres to standard binary addition rules, including handling canary bits and producing correct sums. So this is the block diagram for 4-bit addition. You can see that we are using 4 full adder, and there are 4 inputs, which is for input 0, input 1, input 2, input 3. And there is also 4 output 2. And this is the truth table. You can see that the truth table is similar to the full adder truth table, which is we have 2 inputs, one carry input, and the output is carry and sum. This is the VHDL code for 4-bit addition. We are using std library, and so this is how the code looks like, and this is the result. You can see that the waveform is perform addition arithmetic, and there is, you can see that the binary number is perform addition. So as the conclusion, the exploration of 4-bit addition within the context of digital design provides a valuable foundation for understanding fundamental arithmetic operation is binary. The 4-bit adder, as exemplified through the VHDL implementation, presents a crucial building block in digital circuits, facilitating the addition of two 4-bit binary numbers with efficiency and precision. The architecture of the 4-bit adder, which with its combination of logic gates and parallel processing showcase the intricate nature of digital arithmetic.
I will continue for part 4-bit subtraction. Firstly, for the introduction of 4-bit subtraction in VHDL, performing a 4-bit subtraction involves processing two binary value to produce a 4-bit difference and a potential borrow out bit. The input are minuends and subtrahend, resulting in 4-bit difference and borrow out bit if necessary. For two complement representation is commonly used for handling negative result. It crucial to manage overflow and underflow in fit with representation like 4 bits. The choice between structural and behavior implementation depends on design needs. Designers often use a modular and hierarchical approach for readability and maintenance. Testing, including test bench creation, is vital to ensure accuracy and resilience in various scenarios. The overview emphasizes key component and consideration for systematic 4-bit subtraction in VHDL. This is the objective for 4 bits subtraction. Firstly, we create a subtraction circuit that correctly compute the difference between the specified 4-bit minuend and subtrahend using a normal binary arithmetics. Second, create an efficient digital circuit that use little resources while performing the subtraction operation. This also entails optimizing the logic to decrease delay and improve overall. Lastly, ensure that the 4-bit subtraction module interface effectively with other VHDL component or system that require subtraction. For methodology, 4-bit subtraction in VHDL, 4-bit subtraction can be done through the true complement subtraction or direct subtraction. Two complement involve converting the subtrahend and adding it into the minuend using an adders. Direct subtraction uses full adders for each bit position. Factors affecting reliability include overflow detection and adjustment for signed or unsigned number. Implementation in VHDL involve coding this step using a structure like process statement and component instantiation for adders. The choice between technique depends on design needs and consideration of efficiency, signed versus unsigned arithmetic. The flowchart illustrates the process of performing 4-bit subtraction by emphasizing the conversion of subtrahend of two complement that use of 4-bit adder to obtain the final difference. Firstly, input. The process begins with the user providing the minuends A and subtrahend B as input. Second, convert B to two complement. The subtrahend B undergoes a conversion process to two complement form. Each bit of B is inverted, flip from 0 to 1 and vice versa. 1 is added to the result bit by bits. It's simulating the addition of the binary number 1. Third, fits A and the converted B into a 4-bit adders. Both of minuend A and the converted two complement of subtrahend B are fits into a 4-bit adder. The binary adder performs the binary addition, taking into account to the two complement representation of B, and get the input, get the output. The output of 4-bit adder represent the difference between A and B, which is the desired result of the subtraction operation. A decision point check for the overflow by comparing most significant B MSB of the result with MSB of A and B. If the MSB of the result is not equal to the MSB of A and B, it also indicates an overflow condition. The process can take appropriate action For example, flagging the overflow. Different overflow flag as optional. The final output include the different obtained from the subtraction. An overflow flag may be provided as a part of output indicating whether an overflow occurred during subtraction. The flowchart outlines a systematic process for the performing 4-bit subtraction using a series of full adder for each bit position. Firstly, for input, the user provided the minuend A and subtrahend B as input. Second, for initialization, the carry in or cin for the most significant bit MSB. Full adder is initialized to 1. The step ensure that the subtraction process begin with the assumption of the borrow. Third, for the each bit position, I equal 3 to 0. The process enter a loop to perform the subtraction for each bit position from the most significant bit to least significant bit LSB. Inside the loop full adder instantation, for the each bit position, A full adder is instant with input. Minuend bit AI, the corresponding bit from the minuend A. Then inverted subtrahend bit B as BI. The complement bit from the subtrahend B. And also lastly carry in from the previous FA full adder, cin, the carry out from the previous bit position. The full adder also calculate the sum bit SI and generate the cout. For the output different and overflow flag also as optional. The output from the each iteration of the loop include the sum bit SI, which contribute to the forming the final difference. In additional and optional overflow flag may be generated. Next, for the VHDL code for 4-bit subtraction. Firstly, about library. This line include necessary VHDL library. Standard logic 1164 is used for standard logic type, and standard logic unsigned is used for performing unsigned arithmetic operation. Second, for the entity declaration. This declare an entity named as subtractor 4-bit with 3 port. A and B are 4-bit input vector representing the minuend and subtrahend. Q is a 4-bit output vector representing as a result. Thirdly is architecture implementation. This declare the architecture names RTL for the entity subtractor 4-bit. Next, process statement. Process statement begin. It is sensitive to change the A and B input vector. Next, for the result initialization, the result vector Q is initialized to all 0. Then the subtraction operation is performed using the operator subtracting vector B as a vector A. The result is assigned as a vector Q. For the test bench code, firstly about the entity declaration. This code declare an empty test bench entity. Second, architecture implementation. This declare the architecture name TB for the test bench entity. Thirdly, component declaration. The test bench include the declaration of the component name subtractor 4 bits, represent the 4-bit subtractor. It specifies the input port A and B and the output port Q. For the signal declaration, signal A in, B in, and Q out tests are declared to be used for the test input and output. For the component instantiation, the subtractor component is instantiated as DUT, device under test, connecting its port to the declared signal. For the test process, the main process within the test bench set input value A in dan B in, wait for the short periods, and check if the computed output as a Q out match the expected result. If not, an error message is reported. Test ban also fast condition with a test done. Messages indicate the completion of the simulation. This is the simulation result for the VHDL code and test bench code for 4 bits subtraction. The VHDL code is a simple 4-bit subtractor and the accompanying test bench simulate and verify its functioning. The simulation result is based on the test bench. For example, for the test case 1, subtracting 000 from the 000, input A 000 and input B 000 also, and the expected result for the Q out is 0000. The subtraction of 0 from 0 should result in a 0. This case check if the subtractor produce the correct output for this scenario. For the test case 3, subtracting 0010 from the 1001, input A as a 1001, B in a 0010. The expected result is 01111. The test the subtractor ability to handle a larger number and generate the correct binary result for a positive subtraction. For the test case 4, subtracting 1011 from the 1100. Input A 1100, B is 1011. The expected result is 0101. The test check the subtractor ability to handle the situation where the result is negative, and it also check if borrow handling is correct. Lastly, for the conclusion of the 4-bit subtraction, the VHDL code and test band exhibits a 4-bit subtraction circuit using a structured approach. Employing a separate subtractor for each bit, the design emphasizes direct subtraction, while not the explicitly implement the two complement. It efficiently demonstrates the process. The approach aligned with conclusion, highlighting careful design decision and adherence to the principle. The test bench ensure the reliability through a diverse scenario, affirming the circuit efficiency. In summary, the implementation follows some principle, utilizing a structured approach, a direct subtraction for an efficient 4-bit circuit, underscoring the importance of practical consideration. And
Okay, for the last topic is 4-bit multiplication. A multiplexer or MUX is a foundational component in digital electronics, essential for data transmission and information processing. It efficiently consolidates multiple input signals into one output, optimizing resource utilization and simplifying circuit designs, analogous to a traffic cop for electrical signals. Multiplexers' role in directing information streams enhance data transfer efficiency in various applications. The 4-bit multiplexer specifically selects and routes data from 4-bit input lines to a single 4-bit output line by offering versatility in managing somewhat complex data streams. So, widely used in digital systems such as memory, communication, and microprocessors, the 4-bit multiplexer plays a crucial role in streamlining circuits and improving data transmission. The main objective of using a bit multiplexer is to efficiently combine or select binary data from multiple sources and transmit it through a single output line based on a control signal. So this serves several purposes. The first one, to reduce signal path, which can simplify the systems and reduce the number of signal paths needed, which can lead to lower power consumption. Next, to control data routing signals, which the input data source will be transmitted through the mux to the output. And the last one, to maintain a bandwidth efficiency that enables the efficient utilization of available resources. Okay, for the methodology, I describe it in the form of a flowchart to make it easier to understand. So by referring to the flowchart, the multiplexer design process begins with specifying bit width, input segments, and control lines. Then a detailed truth table is created to outline expected behaviors, and Boolean algebra is used to derive a logic statement, further simplified with a kernel map, K-map. Then a logic circuit is crafted using AND, OR, and NOT gates, and a schematic is drawn. Then simulations validate functionality under various conditions, and physical implementation is confirmed through comparison with the truth table, and integration into the larger digital system is optimized for speed, power, or space. Thorough documentation captures requirements, schematics, and functional details, ensuring an effective multiplexer for digital system integration. Okay, for VHDL code, firstly is VHDL code. The provided VHDL code defines a 4 to 1 multiplexer with four data input lines, which are A, B, C, and D, and two control signals, S0 and S1. The output denoted as Z is determined by the control signals, where the selected input corresponds to the combination of S0 and S1 values, and the process statement checks the control signal values and based on their combinations assigns the corresponding data input to the output Z. So this straightforward implementation allows the multiplexer to efficiently route data from one of the four input to the output, depending on the control signal values, making it versatile component in digital circuit design. Okay, secondly, for test bench code, this VHDL test bench named TB underscore max evaluates the behavior of a 4 to 1 multiplexer. The test bench instantiates the multiplexer unit under the test and defines stimulus signals, which are A, B, C, D, S, O, and S1. And the process section includes a series of signal assignments to simulate different input and control scenarios. Initially, inputs A and C are set to 1, and B and D are set to 0, while SO and S0 and S1 are both set as 0. Subsequent signal changes simulate different control combinations, testing the multiplexer's response. The test bench provides a structured environment to observe the multiplexer behavior under varying input and control conditions over specified time intervals. Next is the result of simulation. First one was the output waveform. Second is the truth table of 4 to 1 multiplexer. And lastly, the schematic of logic gate of 4 to 1 multiplexer. In conclusion, by constructing a 4 to 1 multiplexer involves a systematic process, including criteria establishment, truth table development, Boolean expression, determination, logic circuit implementation, testing, and integration into a larger digital system. This crucial component enables data selection from four-bit input lines, directing it based on control signals. Verification through testing ensures accuracy, and while optimization may be performed for resource considerations, the 4 to 1 multiplexers fast data selection capabilities enhance overall digital system performance. Thank you.